Two machines built before the home computer are now the most distant objects human hands have ever made. They were designed to last 5 years. They have lasted more than 10 times that. And when they finally reached the place where our sun's reach ends, the boundary we had spent decades drawing onto every chart, they sent back a reading that stopped the room cold. The one signal every scientist had been taught to expect, the signal that was supposed to announce the crossing, never arrived. Tonight, the true edge of the solar system, what the two Voyager spacecraft found waiting there. And why a silence, not a sound, forced us to rethink the bubble we live inside. Start with a fact that is easy to forget. The sun is leaking. It pours a thin, electrically charged wind out into space in every direction at once, a stream of protons and electrons moving at hundreds of kilometers per second. We call it the solar wind, and it does not drift gently. It races outward, faster than any pressure wave can travel through it, carving out an enormous bubble around the entire solar system. Inside that bubble, the sun is in charge. Its wind, its magnetic field, its rules. But the bubble cannot expand forever. Out beyond the planets, the wind runs into the thin gas that fills the space between the stars. And where the outward push of the sun finally balances against the pressure of that interstellar gas, a wall forms. Scientists named it the heliopause, the boundary between the sun's territory and the rest of the galaxy. Cross it, and you have truly left home. But the wall is not the first thing a traveler meets. Long before it, the solar wind hits an inner shock and slams from supersonic down to a crawl, piling up into a thick, turbulent layer of slowed solar gas. Beyond that layer lies the heliopause itself. So the edge was never imagined as a single line. It was imagined as a sequence, an inner shock, then a wide buffer zone, and only then the true boundary. The models even told us how thick that buffer should be. For decades, that wall existed only in equations. Researchers built detailed computer models of it. They predicted roughly where it should sit, what shape it should take, and exactly how a spacecraft would know the moment it passed through. The wind from the sun would fade away. Cosmic rays from distant, exploded stars would surge, and the magnetic field would swing, rotating to a new direction as the spacecraft left the sun's field behind and entered the galaxies. 3 clean signals, 3 boxes to check. That was the prediction, refined over years, written into textbooks. Almost no one expected the test to fail. Because for one scientist, this boundary was not an abstraction. It was a prediction he had made and waited most of a career to see confirmed. His name was Donald Gurnett, a plasma physicist who built one of the instruments riding on both Voyagers. His device did something deceptively simple. Out in the near vacuum of deep space, the thin plasma rings faintly when it is disturbed, like a struck surface, and the pitch of that ringing reveals exactly how dense the surrounding gas is. Denser plasma rings at a higher pitch. That single relationship would become the key to the whole mystery. Years before either spacecraft arrived, Gurnett had done something bold. He used a series of violent solar storms as a kind of natural probe. When the sun threw out a powerful burst, that pulse traveled all the way to the distant boundary and struck it, and the collision sent a faint radio cry back inward. By timing how long that cry took to arrive, he estimated how far away the wall had to be. His number put the heliopause around 120 times the distance from the Earth to the Sun, far beyond the planets, far beyond where many of the grand computer models placed it. Most of his colleagues thought the boundary sat closer. For him, reaching that wall was the goal of a lifetime in the field. The single measurement that would prove the sun's domain had a real, findable end. and that he had pinned its distance from inside a bubble billions of miles wide. So, when the first Voyager began its final approach, Gurnett was waiting for one specific thing. Not the magnetic field, not the particle counts. He was waiting for the ring of the plasma to change pitch. He was waiting for the gas around the spacecraft to suddenly grow denser. The unmistakable jump that would mean the ship had left the sun's thin bubble and entered the thicker gas of the galaxy. He had spent a career building toward that one measurement. And when it finally came, it would settle an argument that had split the field for over a year. Because by the time that signal arrived, the spacecraft had already done something that left scientists openly fighting over a single question. Had it crossed, or hadn't it? Here is what actually happened at the edge, and why it was so strange. First came the inner shock, the place where the racing solar wind suddenly slowed. The first Voyager reached it far out, well past where the models had drawn the line. Then its twin, traveling in a different direction, reached the same shock noticeably closer to the sun. That should not happen to a perfect sphere. If the boundary were a simple ball around the sun, both ships would meet it at the same distance from home. They did not. The first hint had arrived. The bubble was not round. It was pushed in at the front, where the sun plows forward through the gas of the galaxy, and stretched out behind. We were not living inside a sphere. We were living inside something closer to a shape carved by a steady wind. As the first Voyager approached the boundary, the readings began to shift, but not altogether, and not in the order anyone expected. The cosmic rays from deep space started climbing early. The particles streaming from the sun started thinning out. So far, so good. 2 of the 3 signals were moving the right way. Then the spacecraft entered a region no model had predicted at all. The magnetic field lines went perfectly straight and orderly, and particles began racing along them in both directions. Solar particles flowing out, galactic particles flowing in, as if the ship had merged onto a connecting highway between 2 separate worlds. Scientists started calling it exactly that, the magnetic highway. Nobody had known such a place could exist. And then, fairly suddenly, the wind from the sun all but vanished. The particle counts collapsed. The cosmic rays jumped to a high, steady level and stayed there. By 2 of the 3 measures, the spacecraft had crossed. It was out. It was in interstellar space, but the 3rd signal never came. The magnetic field did not rotate. It held the same direction it had held for years inside the bubble. And that absence, that missing swing, split the science community in 2. One camp argued the crossing was real. The plasma had thinned, the cosmic rays had surged. What more do you want? The other camp pointed at the magnetic field and refused to move. No rotation, no crossing. The argument ran for more than a year, with the most distant object humanity had ever launched sitting in a place no one could agree how to name. What finally broke the deadlock was the listening. The instrument Gurnett built caught it. A solar storm, fired off long before, finally reached the spacecraft and set the surrounding gas ringing, and the pitch was high, far higher than anything inside the bubble. The plasma around the ship was dozens of times denser than the sun's thin wind. That was the interstellar gas. That was the galaxy. The density jump was the confirmation, and working backward through the data, scientists fixed the true moment of crossing. The boundary had sat right about where Gurnett predicted, near 120 times the Earth-to-Sun distance, roughly 4 times farther out than Neptune. He had been right for decades, while many of the models had been wrong. There was another twist buried in those distances. That thick buffer of slowed solar gas, the layer between the inner shock and the outer wall, turned out thinner than many of the leading models had insisted it would be. The Voyagers crossed it faster than anyone had planned for. Something about how the sun's bubble meets the galaxy was missing from the equations, and it still is. Even now, there is no full agreement on why that layer is as slim as the measurements keep saying it is. But the missing magnetic rotation was the deeper lesson, and here is what it meant. The field on the far side of the wall, the galaxy's own field, simply happened to point in nearly the same direction as the sun's field at that spot. A coincidence of geometry, nothing more. The signal everyone had treated as the very definition of the crossing was never a reliable signal at all. We had built a rule out of our own assumptions, and the universe had quietly ignored it. When the second Voyager crossed years later on a different path, it confirmed the picture and complicated it. That ship did see its magnetic field shift by a small angle, which proved the field beyond the wall is not uniform. It points one way in one place and slightly differently in another. Two crossings separated by a vast stretch of space already disagreed. We had imagined a tidy spherical bubble with a clean skin. What the Voyagers measured was a boundary that changes from spot to spot, breathes in and out as solar storms slam into it, and refuses to give the same answer twice. More than once, a spacecraft holding still in space watched the boundary wash back over it and then pull away again, as a pressure wave from a distant solar storm shoved the wall outward and then let it settle. The edge of the solar system is not a line you could ever stand on. Ask where it is today, and the honest answer is that it depends on the day you ask. And the gas on the far side turned out to be its own kind of surprise. The space between the stars is not empty, but it is almost unimaginably thin, a better vacuum than any we can build in a laboratory, and yet dense enough, spread across enough distance to halt the entire outward rush of our star. The Voyagers caught something else no one had planned for. Shockwaves born near the sun, rolling outward and washing over the spacecraft long after it had left the bubble behind. The sun's disturbances reach far past the wall that was supposed to contain them. All of this matters for more than a map. That bubble is a shield. It deflects a large share of the cosmic rays that would otherwise pour onto the planets, including this one. Knowing the true size and shape of the shield tells us how much radiation reaches us, how that has changed across the long history of life, and what any future traveler would have to survive. And once a ship passes the wall, the count of those galactic cosmic rays climbs and then holds. Proof that the bubble had been turning a fraction of them away the whole time. From the inside, we could never measure how good that shield really was. Now, for the first time, we could stand on the far side of it and look back. There is talk now of building a successor, a craft designed from the first bolt for this exact journey, faster and longer lived, aimed at pushing several times farther out to map the boundary the Voyagers only pricked. If it ever flies, the people who design it might not live to read its most important results. That is the strange arithmetic of this kind of exploration. The questions take longer than a human life to answer. The Voyagers were launched by people many of whom are already gone, and the engineers who will one day hear their final, fading signal are alive right now. Some of them still children, because the hardest fact the Voyagers delivered is one of scale. After a journey of nearly half a century, they are still only at the very beginning of interstellar space. The nearest star is so far that, at their speed, the trip would take tens of thousands of years. They are not going there. They are simply drifting, the first things we ever built to taste the galaxy directly, sending home readings from a place we had only ever guessed at. And that is the part worth sitting with. We had drawn the edge of the solar system for decades. We were confident. We knew which signal would announce it, and when we finally arrived, the boundary was farther than most of us thought, stranger than any of us modeled, and it withheld the one sign we were certain we would see. The lesson was not that the physics was wrong. The lesson was humility. If we could be this surprised by the wall at the edge of our own star's reach, the nearest boundary there is, then how thin is our confidence about everything past it? So here is the question I keep returning to. If the edge of home still had this much left to teach us, what else have we drawn onto our charts that we have never once been close enough to check? If the edge of home still had this much left to teach us, what else have we drawn onto our charts that we have never once been close enough to check?